Microfilters and central filters in DSL networking. Filters are used to manage the shared nature of copper phone lines. While both type separate voice and data signals, they differ fundamentally in how they are installed and their impact on network performance. Microfilters, inline filters. Microfilters are small, portable devices that plug directly into individual telephone wall sockets. Background, introduced as a self-install solution for consumers to avoid expensive technician visits, often called wires-only service. Internal design, typically a passive low-pass filter consisting of resistors, capacitors, and inductors. It blocks high-frequency DSL signals, above 4 kHz, from reaching the phone while allowing low-frequency voice signals to pass through. Advantages, cost and ease, extremely cheap and requires no tools or technical knowledge to install. Flexibility, users can add or move phones to different sockets simply by taking a microfilter with them. Disadvantages, clutter, every device in the house, phone, fax, alarm, skybox, requires its own microfilter. Signal degradation, multiple filters connected in parallel create bridge taps, which can cause signal reflections and significantly reduce internet speeds, particularly on VDSL2 lines. Central filters, master splitters. A central filter is a single, higher quality device installed at the main entry point, NID/master socket, of the premises. Background, originally the industry standard for DSL, often requiring a professional technician to hardwire the separation of data and voice at the source. Internal design, a more complex, robust filter often incorporating high-pass and low-pass circuits. High-quality versions may include active transistors to refine the signal. Advantages, maximum performance, eliminates internal wiring interference, bridge taps, often resulting in 25 to 45% faster downstream speeds compared to microfilters. Cleanliness, one single device protects the entire house, no filters are needed at individual wall sockets. Disadvantages, installation cost, usually requires professional installation or some degree of DIY wiring knowledge. Static layout, requires a dedicated internal wire to be run from the master splitter to the specific room where the modem sits. Comparison summary, when to use which. Feature microfilters, central filters, low-speed ADSL and simple DIY high-speed VDSL2, G.fast, or homes with many best for setups. Phone jacks. Installation plug into every used socket. One-time install at the main entry. Data rate prone to degradation and drops. Offers the most stable and highest possible speed. Requirement must have one for every phone/fax. Only one device for the whole building. Recommendation, if you are using a 2025 standard VDSL2 or high-speed DSL service, a central filter is strongly recommended to ensure you reach the maximum advertised speeds of your plan. DSL home wiring. DSL home wiring is typically configured in one of two ways. In both scenarios, the primary goal is to separate high-frequency data from low-frequency voice signals to prevent interference. 1 microfilter, distributed, wiring diagram. This is a self-install method commonly used in homes with standard phone sockets. Architecture, the incoming line from the service provider, telco, remains connected to all internal wall jacks. The connection, every wall jack used for a phone, fax, or alarm must have a microfilter plugged in first. The phone connects to the phone port on the filter. The DSL modem/router connects directly to the unfiltered jack or the DSL/data port of one specific microfilter. Visual flow, outside line-master socket-internal wiring-wall jack-microfilter-phone and modem to. Central splitter, NID, wiring diagram. This is a high-performance professional installation that isolates data at the point of entry. It is highly recommended for modern VDSL2 or G.fast services to eliminate internal bridge taps. Architecture, a master splitter is installed at the network interface device, NID, or the primary master socket. The connection, the incoming line goes into the line port of the central splitter. The splitter creates two separate paths, one voice path, connects to all existing home phone wiring, no additional filters needed at individual jacks. 2 data path, a dedicated new wire, often Cat5e/6, is run directly from the modem port of the splitter to the specific room where the modem sits. Visual flow, outside line-central splitter- path A, standard internal wiring all phones path B, dedicated data line DSL modem summary table, hardware comparison feature microfilter setup central splitter setup number of filters 1 per phone device 1 single device at entry wiring uses existing home phone wires requires a dedicated modem line bridge taps creates bridge taps, slower, eliminates bridge taps, faster, installation easy DIY professional or advanced DIY signal performance prone to degradation, up to 45%. Provides cleanest, highest speed. Function block of splitters. A DSL splitter is a passive electronic device designed to isolate low-frequency voice signals from high-frequency data signals. In 2025, Modern splitters are engineered to support the extended bandwidth required by VDSL2, up to 30 MHz, and G.fast, requiring more precise filtering than older ADSL models. One functional block diagram. A standard DSL splitter acts as a three-port network consisting of the following key functional blocks: line port, common port, the entry point for the combined signal, POTS voice plus X DSL data, from the telephone exchange. Low-pass filter, LPF, block, the core functional block for the phone port. It allows frequencies below 4 kHz, voice, to pass while heavily attenuating frequencies above 25 kHz, data. This prevents the hissing noise of data from reaching the handset. High-pass filter, HPF, pass-through block. In microfilters, this is often a simple pass-through that allows all frequencies to reach the modem. In central splitters, a dedicated high-pass filter, HPF, may be used to block low-frequency voice transients and ringing voltages from interfering with the modem's data synchronization. Impedance matching block, a series of resistors and inductors designed to maintain a consistent 600 ohm or 900 ohm impedance, preventing signal reflections, echoes, that can cause data errors. Surge protection block, components like metal oxide varistors, MOVs, or fuses that protect both the phone and the modem from high voltage transients, example lightning or power surges. 2 basic circuit diagram, schematic. Most commercial DSL splitters use a passive LC, inductor capacitor, network. A typical high-quality second-order low-pass filter circuit for the phone side is structured as follows: line, tip, dash plus dash DSL modem, tip, L1, inductor, example 10-15 mH, plus dash phone, tip, C1R1, matching resistor, plus dash phone, ring, L2, inductor, line, ring, dash plus dash DSL modem, ring. Inductors, L1, L2 provide high impedance to high-frequency data, effectively blocking it from the phone port. Capacitors, C1 placed across the lines to shunt any remaining high-frequency noise to ground, or between tip and ring. Resistors, R1 used for impedance matching to ensure the filter characteristics align with standard telephone line requirements. Key design differences: 2025 standards, microfilters, often use a simpler two-stage LC circuit to remain compact and cheap. Central splitters, frequently use a 7th order filter or higher to provide much steeper roll-off, more than 55 dB attenuation, for superior performance in high-speed VDSL2 environments. Real-world DSL splitters in 2025 contain several extra components beyond basic inductors and capacitors to handle safety, signal purity, and modern high-speed standards like VDSL2 and G.fast. 1. Protection and safety components. Real splitters must survive lightning strikes and power surges from the telephone network. Gas discharge tubes, GDT. These are sealed tubes filled with inert gas that ionize during a high-voltage spike, creating a short circuit to divert energy safely to the ground. They are preferred for DSL because their ultra-low capacitance, typically 1.5 pF, does not interfere with high-speed data. PTC thermistor/fuses. These act as resettable fuses that open the circuit if a sustained high-voltage power line accidentally crosses with the phone line, preventing fire or equipment damage. ESD diodes. Small diodes placed near ports to protect internal chips from electrostatic discharge, static electricity, when users plug or unplug cables. 2. Signal refinement and impedance matching. Standard low-pass filters can cause signal reflections, echoes, that slow down internet speeds. Matching resistors. Real splitters use high-precision resistors to match the characteristic impedance of the line, usually 600 ohms or 900 ohms, which is critical for reducing return loss. Ferrite cores. The inductors in high-quality splitters use specialized ferrite cores to prevent saturation, which happens when high DC loop currents, from the phone exchange, cause the filter to lose its effectiveness. Transistors. Active filters. Higher-end active splitters may include transistors to provide a much steeper roll-off, ensuring virtually zero data noise leaks into the voice band. 3. Specialty components for specific use cases. Z-blocker circuits. Advanced splitters, like the Z-blocker series, use additional complex filtering to isolate specialized equipment like home security alarms and satellite TV receivers, ensuring they don't crash the DSL connection during an automated dial-out. Common mode chokes. These extra inductors help eliminate electromagnetic interference, EMI, and radio frequency interference, RFI, from picking up nearby radio stations or household appliances. Summary of component checklist. Component purpose. Why is extra type lightning/surge not in basic functional models, essential for real-world GDT/gas tube protection safety. Handles DC loop. Ferrite cores prevents filter failure under high electrical load. Current transistors. Active signal filtering found in premium splitters for superior noise isolation. ESD diodes. Static protection protects sensitive electronic ports from human contact. In 2025, DSL splitters are engineered to meet strict international standards, like ITU-G.992.x for ADSL2 Plus and G.993.2 for VDSL2, to ensure high-speed data coexists with traditional voice services. The filtering characteristics are defined by two primary components, the low-pass filter, LPF, for the phone and the high-pass filter, HPF, for the modem. One low-pass filter, LPF, characteristics. The LPF ensures that high-frequency DSL data does not reach the telephone handset. Parameter typical value, ADSL2 Plus, typical value, VDSL2/2025, passband 0 Hz to 4 kHz 0 Hz to 4 kHz cutoff frequency 4 kHz to 10 kHz 4 kHz to 12 kHz stop band, start, 25 kHz 25 kHz stop band attenuation 45 dB, above 25 kHz, 55 dB, up to 30 MHz, insertion loss 0.3 dB at 1 kHz 1.0 dB, across 0 to 4 kHz, group delay distortion 100 µS 150 µS stop band. In 2025, the stop band must extend much higher up to 30 MHz for VDSL2 or even 106/212 MHz for G.fast to prevent ultra-high frequency noise from affecting the voice line. Attenuation, high attenuation, 55 dB or more, is critical to prevent crosstalk where the modem signal is heard as noise on the phone. 2 high-pass filter, HPF, characteristics. The HPF protects the DSL modem from low-frequency voice signals and high-voltage ringing transients. Parameter typical value, 2025 standard, passband 25 kHz to 30 MHz, or higher for G.fast, cutoff frequency 16 kHz to 25 kHz stop band, voice, 0 Hz to 4 kHz stop band attenuation 30 dB, at 4 kHz and below, insertion loss 0.25 dB to 0.5 dB in the data band return loss 14 dB, to prevent signal reflection/echoes, insertion loss. Real-world splitters in 2025 maintain extremely low insertion loss, below 0.4 dB, in the data band to ensure maximum synchronization speeds for the modem. Roll-off, sharp roll-off, example 70 dB/GHz in advanced designs, is used to clearly separate the voice and data bands, which is essential for stable high-speed connections. 3 key design factors. Transition band, this is the narrow region between the pass band and stop band. Ideally, this band is as thin as possible to maximize usable spectrum. Impedance matching, splitters must match the complex impedance of the phone line, often 600 Ω or 900 Ω, to maintain a high return loss, which directly correlates to fewer data errors and higher attainable speeds. DC transparency, unlike many electronic filters, the LPF must be DC transparent to allow the 48V, 52V DC power from the exchange to reach the phone for operation.